Alright, so here I have a JPEG of a cat, which my girlfriend said looks like me. And I drew my glasses on the cat, just to like really complete the resemblance. So I have this JPEG file, and it's some sort of data that tells my computer how to display this image of a cat. What is the image, what is the information that's being stored in a JPEG file? And can we try to represent it mathematically? Well, here's a Python script which opens up the JPEG. So we want to use the matplotlib library's image package, which deals with how to read images. And we'll use this imread function, which reads in images like JPEGs and PNGs, and we convert it to a array. So an array is somehow just a big list of numbers, right? And we're going to look at this array's shape, and we're going to look at what's actually in the array, and we're going to plot it as a picture and show the picture. And that way we can try to understand what exactly is being stored in a JPEG file. So if we run this code, we get our outputs here. So in the text part of the output, we have the shape of the array, like I said. It's 1024 rows by 1021 columns, and then in each row and column we have 3 numbers. And 1024 by 1021 is just the resolution of the image. If we look at the file information here, we can see it's 1021 by 1024. Okay, cool. And then we have 3 numbers in every pixel. So we have exactly like you can see here, 3 numbers in every pixel. And if you know how color is represented on a computer, if you know how JPEGs are usually stored, then you will know that these colors are RGB values. They tell you how red is the color at that pixel, how green is it, and how blue is it. By combining that number, you can represent a lot of different colors, and that's exactly how a JPEG works. It tells the computer, at every pixel, I want you to display the color that has this much red, this much green, and this much blue. So if we look at the other part of our output, which is this this matplotlib library interactive figure, then we can see, okay, we have our axes, which tell us exactly which pixel we're looking at, and if we hover our cursor over any given pixel, we can see in the corner there that it tells us, okay, this is the pixel at point 484, 362, and the color has red 242, green 216, and blue 201. If we zoom in, say on the cat's glasses and eye here, we can see, okay, the glasses have this color 240, 182, 56. The eyeball is 22, 23, 27. The fur is 209, 119, 190, and so on. So now we know what's in a JPEG. A JPEG is just a file which tells the computer at every given pixel you need to display a certain color. How can we represent this mathematically? Well, if you've taken a linear algebra course, then looking at these lists of 3 numbers here in the square brackets might somehow remind you of a row vector, right? Or you can just imagine flipping the numbers and getting a column vector. So maybe we can use our knowledge of vectors in linear algebra to do something interesting here. Maybe we can think of the JPEG as being a file which tells the computer at every pixel you want to display a certain vector, where the vectors are in some sort of color vector space. And then we can ask, well, what does this color vector space look like? So here we have a graphical depiction of this RGB color vector space. And this is not a new idea, of course. If you Google search 3D color space, you will find lots of images like this one. I downloaded this one in particular off the Wikimedia Commons, which I'll link in the description. And I drew on it some RGB axes, right? Because we want to think of our vector space as having a basis R, G, and B as our basis vectors. And on a computer, the values are between 0 and 255, because 255 is like 2 to the 8 minus 1, so it's 1 byte. So how can we depict one of our points here, right? Like we look at the color of the cat's glasses, okay? 240, 183, 70. So let's write that down. 240, 183, 70. And if we try to depict this in our color space, right? So we need to find where the origin is. So if we draw in the axes that go to the back of the cube, we have our origin here. We want to go around 240, which is like roughly here, so on, in the red. Say around here is 183 in the green, and then around 70 or so in the blue. And we want to draw the point that, you know, that is at those 3 coordinates, and we get a vector that is, you know, kind of hard to draw in 3D, but we get an arrow like this, and we can see that we are, you know, we're roughly in the right color range, right? We have our cat's glasses are this nice golden yellow color, and we're approximately in that color. Now, of course, this is not perfect because I'm just drawing it by hand, and we can't really see into the interior of the cube with this picture, but hopefully you get an idea of how we can imagine our colors as being vectors in this way. So if we can think about colors as being a vector space, then that means we can do linear algebra on colors, right? But hold on, not so fast. If we're going to be proper mathematicians about this, we can't just draw some arrows on a piece of paper and say, oh, we have a vector space. We need to check carefully if we actually have something that satisfies the definition of a vector space. So I have the definition here, which I wrote earlier. A vector space over R, the real numbers, is a set V, in this case the set of RGB colors, and operations plus and scalar multiplication, such that for any vectors u, v, and w, or in this case any colors u, v, and w, and any numbers a and b in the real numbers, we have these 8 properties. And most of these properties we can easily check by just using the fact that we're writing our vectors as lists of numbers, like, 171, 51, 0 or something. And we know that adding numbers together is associative, adding numbers together is commutative, and so on. But there's a couple properties that we need to, that we have a little bit of a problem with. So the first one that is a little bit interesting to think about is property 3 here. So it says there has to exist a 0 vector, which in this case we can think of as a 0 color, such that adding it to every other vector is the same vector back. And you might already say, okay, well, this makes sense. We have the vector 0, 0, 0, which is, no red, no green, and no blue, so no color at all, and that's black. And that makes sense. Okay, black is the 0 color. It's the not having any color, which makes sense. But there's a little bit something strange, which is this part here that says that by adding black to any other color, we get back the same color. If you like to paint, say, then this might strike you as a little bit strange, because if we mix black paint with, say, red paint, we're not going to get back the same color of red, right? We're going to get a much darker shade. And so, in one way, this does make sense. In another way, it's a little bit counterintuitive. Then the real problem that we have, though, is this property 4, which says that for every color, there has to exist like a negative of that color, such that we can add them together and get the 0 color, or black. So it's saying there has to be a negative red, such that if we do red plus negative red, we get black. And this is not really, do we have such a thing as a negative red? It's not very obvious to me that we do. And in fact, we haven't really defined, like, what does it mean to have negative 255, 0, 0? If we try to put this in the computer, it's just going to throw some error. It's going to say, well, that doesn't make sense. So we need to kind of solve this question of negatives if we're going to say we have a vector space. But I claim that for now, we can just ignore it and just make sure we always have positive values and do some linear algebra. And then once we have a little more understanding of what we're doing, we can try to answer the question of negatives. In order to do linear algebra on our JPEG files, I've got another Python script here. So as before, we will import some libraries, the matplotting library, numerical Python. We will read our picture, convert it to an array, print the shape. Now we're going to make 2 horizontal plots so we can plot the original image, and then we will afterwards plot our edited image. So we have our function, which is called apply transformation, and it takes in the data for the image and a linear map L, linear transformation, if you will. And what it does is, as the comment says, at each pixel, apply the map. So we make a copy of the data, we iterate over all of the pixels, and at every v, which is the color vector at a given pixel, we matrix multiply our matrix L with our vector v. And then finally, we have to clip the values to be within 0 to 255 because, for example, our matrix, say we multiply by 10 in the matrix, we might get some large number that the computer can't display, so we have to crop it, unfortunately. And we set our new image's ijth pixel to be the value of this matrix vector multiplication. Then we return the new data. Here we define what matrix we're applying, so right now I have just the identity matrix, so it wouldn't do anything at all. And we display the result on the same figure as our original image. So let's try to do something interesting here. So the first thing I want to try is what happens if we rotate around the diagonal in our color space. So what if we do the rotation that sends red to green, green to blue, and blue to red? How would we do that? Well, we know that a matrix acting on a basis vector, like if you act on the first basis vector, you get out the first row of the matrix, because if it's 1, 0, 0, it's 1 times the first row, 0 times the second row, 0 times the third row, and so on. So if we want to send red, which is the first basis vector, 1, 0, 0, or 255, 0, 0, you might say, to green, then we need to send to 0, 1, 0, because we want 1, 0, 0 to, which will give us this row, and we want it to be green, which is 0, 1, 0. We want to send green to blue, which is 0, 0, 1, and our third one is blue, which we want to send to red. Okay, so we punch in this linear map, we run the code, and we get... So the computer did exactly what we asked. It took at every pixel the vector that represents the color of that pixel and multiplied by the matrix which we had defined in our code. And we can see that it does exactly what we wanted it to do. We took the color red, we sent it to green. We took the color green, we sent it to blue. We took the blue, we sent it to red. And we see that the combined colors in the interior gets like all rotated as well. White and black are unchanged, as you might expect. So very cool. Our geometric intuition about what's happening matches up with what happens when we just do the transformation. Okay, so we can ask like, okay, sure. So this color wheel shows that our intuition is correct, but it's not a very interesting image to look at. So maybe instead we run the code for the cat picture, right? So we change rgb.jpg to p.jpg, which is the name of the cat picture. We run it again. Okay, so we get out our image here, and we can see our original cat picture has a lot of orange and yellow tones, right? And those got rotated to green and cyan because red got rotated to green and yellow got rotated to cyan in the original transformation. So we get this nice color shifted cat. Okay, so here's one that I did a little bit in advance. We can ask, what is our scalar multiplication doing in our vector space? So here I took the cat image, and on the top I applied the matrix 1/2 times the identity, so it's just a diagonal matrix with 1/2, 1/2, 1/2 on the diagonal, and we see that it just dims the image by 1/2. And on the bottom, I did the same thing, but instead of 1/2, I do twice the identity, so it's a diagonal matrix with 2, 2, 2 on the diagonal, and it brightens the image by twice as bright. And so scalar multiplication is just a brightness factor, which scales the brightness of the image. Very nice, that's cool. Now we know maybe how Photoshop does brightness filters, perhaps. And as one more example, we could try what happens if we delete the red out of our image. Okay, so here we have one that we take every vector and we apply it by the matrix shown here. So what it does is it does nothing on the green, it does nothing on the blue, and it just multiplies the red by 0. So send all the red to 0, delete the red out of the image. And probably looks like here the RGB chart we see, we're just literally deleting out the red. It's as if the color red just doesn't exist anymore. And we see that this is what the world would look like in a world where we had no red. So with this small program, with just a little bit of, we don't really, I know almost nothing about computer graphics. I know very little about computer programming. But with just a little bit of linear algebra, we're able to recreate a bunch of color balancing filters, brightness, and stuff like that you might see in a tool like Photoshop. Now that we have a little bit of an understanding of what's going on, let's try to tackle the negatives, the question that we said we will leave for later. All right, so we want to try and, so what we're doing here really is we're trying to develop a model, a mathematical model of color, right? And a model is no good if it doesn't match reality. So one thing that's always good to do is to write down some properties that our model should have based on our understanding of color in reality, and try to write down a model that matches those properties. So what properties should we want negative color to have? Well, the first thing I want is that negative white should be, the opposite of white, and the opposite of white, as probably anyone would agree, is black. So I want negative white should be black. And similarly, by multiplying both sides by -1, we need to have white is negative black. Okay, this is the first property I want my model to have. Now the second property is that, the whole idea behind me writing this code in the first place was that I wanted to think of color as a vector space and then imagine doing geometric transformations like scaling and rotation in order to do filters on images. So this whole picture is broken if my model does not preserve this geometric intuition. So we want geometric intuition to work. So we want to define negative color in such a way that we have these two properties. Or at least I claim that my model of negative color should have these two properties. There is, of course, probably lots of other ways you could do it that would give you a different model. So here's the model I propose that will have these properties. We take our color space from before. So if I draw on some axes, so our color space was this cube on the interior of these coordinates, right? We had 255, 255, 255, where this is red, green, and blue. And we have this cube in the positive section of our XYZ plane. And what I want to do is I want to shift everything over. So I want to shift everything over by the vector 127.5, which is 255 over 2, 127.5, 127.5. And what that does is we take all of our we take our color space and we move everything over by this vector v0. So this is v0. So we get a new picture which is like this. We have our axes as before. R, E, G, and we've taken the cube and we've shifted it so that now it goes below, goes like, you know, kind of hard to draw in 3 dimensions, so don't judge me too much. But we get something like this, right? Where now the origin is in the center of the cube, and we have the cube extending into the negative parts of the axes. And now our edges of the cube, instead of being 255, they're 127.5, 127.5, 127.5. And the range, so now we can go into the negatives, and we have negative 127.5 on each axis. So this is how I want to define negative color. I want to say that essentially the color that I get by applying this transformation is negative color. Or another way of saying it is, once I have a color in this space, I have to apply the opposite of the transformation. So instead of subtracting 125, I have to add 125. And I've defined what the negative color is. So I'm saying that negative, I should say it like this. If I have some value here, like negative 10, negative 25, and negative 51, then this corresponds to the color, which I get by adding 127 to each of these. So I get 137, and 132, and 178.5. There we go. So this satisfies our geometric intuition model because we're literally just geometrically sliding the cube over. Then we can apply all of our intuition on the cube and then geometrically slide it back to get our image. And it also satisfies the property we wanted about white and black, because in this model, white, which you might remember was this top corner of the cube, gets shifted to, so white gets shifted to 127.5, 127.5, and 127.5. And black, which was originally the origin of the cube in the bottom, in the back corner, it now gets shifted to minus white, which is 127.5, minus 127.5, and minus 127.5. So what we're doing is we're saying, okay, our space is not a vector space because we don't have negatives, but we can make a vector space by shifting our space, our color cube, by just this vector with entries 127.5. Then we can do all of our linear algebra there. And in order to get an image back, we have to undo the shift because our computer does not really understand what negative colors are, right? So As an equation, what we're doing is we're simply saying, all right, instead of just taking a vector v and a linear map L and saying we do L times v, we're saying we take a vector v, we apply our shift by this v naught, the 127, 127, 127 vector, then we apply L, and then finally we do v naught. And this is our new model, okay? And I claim to those who have learned a little more than just first year linear algebra that this is like exactly equivalent to thinking of our vector space as being like essentially a free Z mod 255 module. Okay, so let's modify our code to do the shifting, and then we can ask what the negative of colors and the negative of an image is. So here's the modified code, which applies this shifted way of thinking of the color space. So it's all the same as before, except for this apply transformation function. So I want to apply the transformation by this 127 divided by 2 vector that we talked about, but I don't want to have any fractions. I want to do everything in the integer, so I'm going to multiply by 2. So instead of shifting by 127.5, I'm going to shift by 255. So I take my vector as from before, the the entry of the JPEG at that point. I multiply the color by 2, and then I subtract 255, which is this is applying the shift by this vector, so that we have our cube centered centered at gray. We apply the transformation at every pixel. As before, we just matrix multiply, and then we uncenter. So we subtracted this 255 vector, so we need to add the same vector back and then divide by 2 because we multiplied by 2. As before, we crop the RGB values and then we save it into a new image. So we can use this and we can try doing like a negative transformation now. So if we do, first thing I want to do is just like, what's negative 1 times the image, right? What is the negative of an image? And if you're familiar with like, Photoshop or whatever, you probably already know exactly what's going to happen here. But if we apply the negative of an image, so we applied our -1 transformation. We got the negative of this image, which is this image. So we took our RGB Venn diagram and we got a CMYK Venn diagram because red went to cyan, green went to magenta, and blue went to yellow. And there's probably something very deep going on here because this is like, RGB is the additive color theory where you get colors by adding red, green, and blue, and CMYK is the subtractive color theory where you get colors by subtracting cyan, magenta, and yellow from each other. And we're doing negative, so we're sending adding to subtracting. So that's kind of interesting there. And I don't know enough about color theory to say if this is some deep fact or something relatively simple. But what I do know is that we have essentially recreated this well-known thing called the negative of an image. So here I have the Wikipedia page for negative photography. And you might ask, hold on, we just spent like 25 minutes to basically get the second paragraph of the Wikipedia page for negative? Yes, that's exactly what we just did. In the case of color negatives, the colors are reversed into their respective complementary colors. And if we click into the Wikipedia page for complementary colors, we see that in the RGB color model, we get exactly the same thing as what we just derived. So did we learn anything more interesting than just that the term negative of an image is a pretty good name for it? Well, originally I was writing this code as a way to try and show my first year tutorial students that linear algebra can be applied in a lot of contexts that aren't obviously mathematical, because we don't usually think of color as being some sort of mathematical object. But it turned out more of an exercise in modeling the real world mathematically, and then looking at the results of your model, seeing its limitations, and figuring out what you can learn about the real world by applying math. There's so much more we could have done with this model now that we've written it down and figured out how it works. Sure, we were able to get a few of the common color filters and stuff that you would see in a tool like Photoshop, but there's a lot of different matrices we didn't apply, and we could have seen if there's any other interesting filters that are not commonly included. You could even get really fancy and start like asking about cross products and dot products and stuff like that, as one of my students brought up when I showed this to them. Or if you wanted to go really crazy, you could even say that a JPEG is just a section of the trivial R3 bundle over a subset of R2, and then try to do like differential geometry JPEG applications or something like this. And I'm far from the first person to think about color theory this way, right? If you Google search RGB color space theory, you can read further. There's like entire courses on this topic in image processing and stuff. And there's even nonlinear color theory. But I'm not trying to take another 25 minutes of your time. However, if you do have any cute ideas, you can put them down in the comments, and we will discuss them and see if we can learn anything more from this model. But really what I hope you take away from the video is not anything about color or linear algebra, but just that we can use math in lots of fun ways to explore the world around us. We can just take a concept or an object and try to say, what is this object represented by mathematically, and what do our mathematical theorems tell us about this object? And really, I mean, that is the point of learning math in the end for many people, is just to understand reality, right? So thanks for watching, and I hope you guys have a great day.